Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Applied Thermodynamics, Module 4, Gas Turbine Engines. So, previously on this module, we have discussed 3 lectures, that is gas turbine engines, components, thermal circuit, gas turbine performance part 1, turbine performance part 2, and just to emphasize the fact that when we are talking about this gas turbine performance, we mainly concentrated on power generation through gas turbine engines. But apart from that, the other application for this gas turbine engines is in the aircraft propulsion. So, we will move to aircraft propulsion cycle in the subsequent class, but before you do that, we must understand some other concepts, that how the real gas turbine performance cycle is differs from the original cycle. By original cycle I mean that the very basic cycle for gas turbine engines is the Brayton cycles, and on top of that we introduced the modified cycles in terms of intercooling, reheating, reheat and intercooling with a combined performance. But when you move to aircraft propulsion cycles, our main intention is thrust generations, not power. Now, in the process of thrust generations, we expect the working fluid has to circulate within the circuit, and those circuits involve the components like compressors, turbines, combustion chamber, and these compressor and turbines are called as turbo machines, and when they circulate, they have substantial velocities while crossing those components. One very good assumption could be that those velocities can be neglected. I mean, the energy content due to the kinetic energies of the fluid can be neglected as compared to turbine work or compression work. But when you do propulsion cycle, this velocity has a significant value, one cannot ignore. So, this is the very basic difference, that when a gas turbine engines runs in a thrust mode, where the velocity components are significant in terms of total energy. So, in our particular topic today, that is real gas turbine performance cycle, which we will be discussing, we will debate on those aspects, that how a real gas turbine cycle is different from its air standard cycle. So, on this lecture, the following topics will be covered. So, we will introduce the component losses, and since we are dealing with mainly, because we will be focusing in subsequent class on aircraft propulsions, where we will be looking at some properties which we call as stagnation properties of the fluids. So, these things we will discuss, that how the stagnation properties of the fluid will help us in quantifying the losses at different components. So, these are the 3 significant headings of today's discussion. So, let me start. First thing is that component losses. So, the very basic cycle that gas turbine has, compressor, turbine joined together with a common shaft, in a sense that turbine drives the compressor and fuel gets added, and out of this, after expansion, we get power output or thrust. So, here your main intention is thrust. So, in this is what the simple gas turbine operate, but when you are looking at the component losses, what are the different sources of losses? So, let me start one by one. The performance of real gas turbine cycles differs from the ideal cycles due to various component losses, and this accounting of these losses needs to be quantified. And since the compressor and turbines are commonly known as turbo machines, and they are fundamental units of gas turbine system. And as I mentioned, when you deal with the mainly in propulsion system, the fluid velocities are generally very high when they pass through compressor and turbine. So, because of this, the changes in the kinetic energy between inlet and outlet of these components cannot be ignored. So, the compression and expansion process in this compressor and turbines, they are mainly irreversible adiabatic, and of course, they involve increase in the entropy. And of course, the fluid friction results the pressure losses in the combustion chamber and heat exchanger. In fact, when a heat exchanger is incorporated, it involves pressure losses. Another issue is that when the entire idea of this heat exchanger is that we have to preheat the compressed air coming out from the compressor to a upper limit where the turbine exhaust gas has. So, means in a sense that looking at the TS diagram, the available temperature difference is T5 minus T6, but that is the maximum available temperature difference, but unfortunately due to pressure losses in the heat exchanger, then we are not in a position to capture this total heat content with these available temperatures. So, in a sense that the compressed air cannot be reached to T5 temperature, rather it terminates at T3, whereas turbine exhaust temperature cannot reach to T2, rather it remains at T6. So, this is what the heat exchanger effectiveness comes into picture. So, there is likely to be a terminal temperature difference. Apart from that, bearing and windage friction in the transmission process. As you see is this, that the turbine drives the compressor. So, so it means that during the transmission of power from turbine to compressor, there is other type of losses, that is bearing and windage. This needs to be accounted. Now, apart from that, there are values of Cp and gamma. So, we will see in this sense that in fact in last class also we mentioned that the Cp and gamma, they when you take the hot gases in the turbine, its value is different because they involve chemical compositions and high temperature changes. So, because of this reason, we have to take the variation of Cp and gamma, and of course, in some sense Cp and gamma also varies with temperatures, and in the entire gas turbine units the complete cycle has routinely the temperature of the cycle routinely changes. Another issue could be that heating value and composition of the fuel are not taken into account in the ideal cycles. There what we just simply said that we just added heat in terms of fuel, but fuel has no role except it just adds heat to the system. But when you actually take the quantification of how much fuel is added, then we should be worried about specific fuel consumptions. That means how much fuel you require per unit work output. So, all these things needs to be accounted. Apart from that, we also to quantify these specific fuel consumptions, we also have to assume that there is some combustion efficiency. That means fuel has certain energy which we call it as a calorific value. Entire calorific value of the fuel is not recovered, almost 98 or 99% of the fuel gets combusted. So, when by assuming a combustion efficiency, we allow incomplete combustion. So, this is also a part of component losses. And second thing is that when you say another issue could be that when during this combustion process we add fuel into the air. So, that means mass flow rate in the turbine is different because the compressed air comes from the compressor. Till that point of time there was no fuel. Now, in the combustion chamber fuel gets added. So, by virtue of this the mass flow that enters into turbine is different than that of compressor. So, the virtue of the fuel addition, the mass flow rate in the turbine is greater than that of compressors. Another important issue is that in the gas turbine engines, the turbines are turbine blades are typically exposed to the highest temperature. That temperature could be 1350 Kelvin in the order of or more than that. So, it means that in a continuous operation, the blades are likely to experience the very high temperature, and we call this kind of phenomena as thermal endurance, and with time the quality of the blade or blade quality degrades. To have a longer lifespan of the blade, we must cool the blades continuously. So, that means internal cooling is allowed through the blade route. So, we call this as air cooled blades. Now, from where this air will come from? This air normally comes from the compressors. The combination of the stator, rotor and disc parameter from the compressor, some of the compressed air is bypassed to the turbines just for the cooling purposes. So, this is that means a total about 15% of the compressed air delivery goes as a bleeding, and this phenomena we call as a bleed flow or bleeding, and this bleed flow why do we require? Just to cool the turbine blades. So, in a sense that we must allow this fact for a continuous operations, and for that reasons we have to add some extra mass in terms of fuel. So, this fuel air ratio is in the range of 0.01 to 0.02 gets compensated or gets added to counter of amount for this kind of bleed flow. So, whatever I have discussed, all these issues need to be accounted, and we call them as a component losses, and that has to be incorporated in a real gas turbine cycles. However, some of these losses we can do it mathematically or do it by incorporating by simple changes, and some of the things we get the information through continuous experimental data. So, based on that, based on those observations, the losses are quantified. Okay. Now, the next section that we are going to discuss is the stagnation properties of the fluid. So, why we introduce the stagnation properties of the fluid? Because of the fact that the first important information that aircraft propulsion system has, it uses turbo machines, and it has like compressors and turbines. So, entry from the entry and exit state of the components, turbines and compressors, they have essentially very high velocities. And when you say high velocity, they also has certain kind of energy, and we call this as a kinetic energy. And in fact, this kinetic energy is a significant contribution as far as the total energy is concerned. Now, to account for this fact, so instead of so when you actually say the temperature is whatever we measure, that is due to the static temperatures, but that temperature does not account due to this kinetic energy or velocity associated with the flow. So, for that reason we implicitly define a properties which we call hypothetically we call as stagnation properties, and they implicitly use these velocity components. How? So, let us explain that. So, the kinetic energy in terms of steady flow energy equation can be accounted implicitly by making use of the concept of stagnation or total enthalpy. So, in a physical sense, stagnation enthalpy of a flowing stream is the enthalpy that it possesses when the flow is brought to rest adiabatically without heat transfer. For example, if you have some kind of properties, that means for example, if you look at this particular figure, we have a reservoir, it contains total energy, and that energy we say in terms of which is stagnation temperature, we can say it is a stagnation pressure, you can say in terms of stagnation density, and we allow and that reservoir, and we can from this reservoir, because it has total energy constant, by appropriating suitable diverging section, we can accelerate the flow. Or in other sense is that when the flow is already in accelerating stage, that means we can decelerate in such a way that we can bring it adiabatically and without heat transfer to rest. So, for a given arbitrary systems, if you have initial state, we can accelerate isentropically to a final state, and when you are in the initial state, and we can decelerate the flow isentropically to the final state. So, now I am putting this stagnation enthalpy in the reverse definitions, that already the flow is in the has certain velocity, certain pressure and certain temperature. We are decelerating the flow to the final state, so that its velocity becomes 0. Now, in those case, if you want to refer in this enthalpy diagram, and there are two, and when you have this, that means if you have the flow has certain enthalpy, and if you are at certain enthalpy, and at that point at a certain pressure. So, if we can define another parameter, what is called as a stagnation enthalpy, which is much higher than this. That means, by introducing a velocity component here for a given flow at an arbitrary state, for that particular state another property can be defined, that is represented as stagnation state. So, in a sense that at any arbitrary state, if your enthalpy is h, its stagnation enthalpy could be defined as h naught by introducing these velocity components. Similarly, the stagnation temperature is T, the corresponding the static temperature is T, corresponding stagnation temperature would be T naught. Now, how do you do this mathematically? Let us see here. Now, you recall the steady flow energy equations, Q is equal to H2 minus H1 plus half C2 square minus C1 square plus W. So, basically heat transfer Q, W is the work transfer, change in enthalpy and change in the kinetic energy. Now, what you do is that, now if you apply this equation at two different states, one at stagnation state, other at arbitrary states, and without any work and heat transfer, these equations can be represented as H naught is equal to H plus C square by 2. So, without heat transfer and without work transfer, enthalpy can be represented as H naught is equal to H plus C square by 2. So, implicitly if you define as H naught, it accounts for static enthalpy, it accounts for the enthalpy associated with the kinetic energy. And then we can simply express enthalpy in terms of Cp times T naught. So, T naught becomes your stagnation temperature, whereas T remains the static temperature. So, the dynamic temperature becomes C square by twice Cp. So, from this enthalpy expression we can define as the stagnation temperatures. Now, moving further, going for another situation, that from these equations another way of representing the steady flow equations is adiabatic compression situation and heating process without work transfer. What we can say is that that steady flow energy equations, another way of representation of the steady flow equations can be in the form of adiabatic compressions, and for that process instead of static temperatures, and we can also represent in terms of stagnation temperature. So, in earlier compression system we used Cp in a compression is Cp times T2 minus T1, but here the way of representation would be T02 minus T01. So, in similar sense we can do the heating without heat transfer could be Q is equal to Cp times T02 minus T01. So, now in by defining this state, stagnation state, we can just revisit the temperature entropy diagram when there are two states 1 and 2. So, there are two practical states, that means a system undergoes a compression system compression process from state 1 to 2. Now, for this state 1, the hypothetical way of representing its stagnation temperature as T01, and for that stagnation pressure stagnation temperature, the stagnation pressure would be P01. Now, when the system is at 2, the corresponding stagnation pressure would be P02, and corresponding stagnation temperature would be T02. So, in a sense that we can define this for any arbitrary states, we can define its corresponding stagnation states by accounting the velocity factor. So, in the first case when it was state 1, its velocity factor was c1 square by twice Cp, and its in second case the velocity factor is c2 square by twice Cp. And by doing this, another expressions that we can derive, that by defining the stagnation temperature T naught square by T is equal to 1 plus C square by twice Cp. So, here you use this Cp as is equal to gamma r by gamma minus 1. Now, here you can write this gamma r t as a is nothing but speed of sound. So, a speed of sound is normally defined by square root of gamma r t, and by taking the ratio of speed of the body or velocity of the fluid to the speed of sound, we now represent the stagnation temperature in a parameter which is m, and we call this m as Mach number. So, this Mach number of the fluid is very vital factor in deciding or in calculating the stagnation temperatures and pressures. Now, having said all these things, one can, when the system goes from state 1 to 2, different isentropic relations can be derived from P02 by P01 and T02 by T01. Another important factor I would like to explain, that from the beginning we assume that the process happens to be adiabatic. Now, what happens in certain situations, if the changes are also associated with change in the pressure, then in such a process can be considered as an isentropic process by defining this stagnation properties. By having said this, when you say the stagnation properties, when the stagnation temperature is employed, there is no need to refer explicitly kinetic energy terms, because it is easier to measure stagnation temperature of high velocity stream rather than the static temperature. So, it is a practical advantage. And in a process, if there is no heat and work transfer, then stagnation temperature will remain constant. So, from that you can see here that when if you from the steady flow equations, when you derive this adiabatic compression, if there is no compression work, if there is no work transfer, then you will see that the process total T02 would be equal to T01, but that does not but when you total temperature remains same, but the static temperature or speed could vary, but the total temperature remains same. Similarly, for an heating process, if total temperature if there is no heat transfer, total temperature remains same, but static temperature and speed could vary. Another aspect that I just want to explain is that prior to definition of the stagnation properties, we also come to know that similar term when you deal with the Peter. That point of time when you deal with incompressible flow, we also say that stagnation pressure of a flowing fluid can be defined by static pressure plus the dynamic pressure, that is P plus half rho C square by 2. But their main assumption was that fluid was incompressible, and that point of time we say it's a P is a static pressure and half rho C square is your dynamic pressure. But that point of time it was the effect of Mach number was not taken into account when the flow is compressible, because when the flow is compressible, density, and that point of time when you say incompressible, role of density is insignificant. But when you deal with the compressible flow, the density changes are so significant that it will also change the stagnation pressure value. So, a typical quantification could be that way, if a stagnation pressure is defined for a compressible flow and for an incompressible flow, for some situations that when you have Mach number of 1, we will find that the from the Bernoulli's equations, we will find this ratio P naught 2 by P as 1.7 and P naught 2 by P will be 1.89. So, there will be about 11% difference or deviations. So, that means that because the Mach number effect was not taken into account when you deal with Bernoulli's equations. So, in a sense that one should not confuse that about this definition of stagnation pressure when you deal with the Pitot pressure or based on the Bernoulli's equation calculation and the stagnation pressure which is calculated from the isentropic relations. So, this is how the we say that, and in fact when you look for the jet propulsion cycle, we normally think about the flow is compressible and for which the Mach number is always more than 0.3, and effect of Mach number becomes insignificant below the value of 0.3. Okay. Now, let us go one by one how to quantify the component losses. First type of loss that we are going to introduce is the isentropic efficiency, and that is for the compressors. So, previously we also defined this isentropic efficiency in our previous lectures, but that was defined in a context of static temperature or pressure, because when you deal with the gas turbine engines with a power generation motive, the terminal velocities at the components, particularly compressor and turbines, and they do not offer significant contribution to the total energy. So, in more or less we simply neglect those numbers. But when you deal with the turbo machines involved in the gas turbine engines for air propulsion methodology, then we have to represent those efficiency, but in terms of stagnation temperatures or pressures. So, this is how we did it, very basic difference, that instead of representing the efficiency in terms of static value, we are going to write them in a stagnation temperature difference. So, first thing, when you say work consuming device, the total work would be isentropic efficiency can be defined as the isentropic work to the actual work. So, isentropic work will be less, so compression efficiency is defined. So, based on that we can calculate the, in a compression system, in a compressor, the total temperature difference T naught 2 by T 1 in terms of component efficiency, that is compressor efficiency. And since it is easy to represent this component, the temperature ratios in terms of pressure, one can represent in terms of the total temperature difference across the compressor can be represented in terms of component isentropic efficiency of the compressor and the stagnation pressure ratio. In a similar sense, when you deal with turbine, one can write the turbine efficiency as the actual work to the isentropic work. So, actual work for a turbine can be represented in terms of stagnation pressure, that is Cp times T naught 3 minus T naught 4 divided by Cp times T naught 3 minus T naught 4 dash, that is isentropic work. So, Cp will get cancelled and finally, we get the turbine efficiency. The in a similar sense, where the temperature difference across the turbine, that is total temperature difference T naught 3 minus T naught 4, and this can be expressed in terms of turbine efficiency and in terms of pressure ratio as well. So, in both way that pressure and temperature are incorporated in the calculations. So, this is how when you deal with actually isentropic efficiency for turbines. But what happens is that in a real sense, when you see the turbines, when they are incorporated in jet engines, the main intention is to recover thrust. So, this turbine which is used in the jet engine is integrated with a nozzle kind of assembly followed by a diffuser. So, since we want to extract as much as energy from the exhaust flow when during expansion process, so typically we get a higher pressure ratio across the turbine, and because we are incorporating them through a nozzle shaped arrangement, first thing. Second thing, we also expect that when the gas or exhaust gas goes out of the atmosphere, its pressure is almost close to ambient. So, that means we incorporate a parameter component what we call as a diffuser. So, what does the diffuser do? It brings the final velocity to a negligible value, so that pressure becomes ambient. But however, we have to just to remember that while dealing with the component efficiency or isentropic efficiency turbine, we still look into the expansion process from T03 to T04. So, this is the actual expansion process in a turbine. Okay. Now, apart from this, there is another way of representing this isentropic efficiency, what we call as a polytropic efficiency. Let us see that we also have isentropic efficiency, then what is the necessity of defining a polytropic efficiency. What has been observed is that if you actually try to plot the when you say isentropic efficiency, it has a fixed value, okay. But when you say fixed value, it has to operate at certain pressure ratio. If you look a wide range of pressure ratio from let us say from 2 to 20, it can be seen that the isentropic efficiency of the compressor varies from maybe from 0.85 to 0.9, and similarly when you go for higher pressure ratio, turbine efficiency increases. So, in a sense that we say that even though we define isentropic efficiency, but it is a function of pressure ratio. So, it means that we are in a wide range of pressure ratio, the isentropic efficiency also changes. So, to counteract this argument, if you have a very wide range of pressure ratio in comparison, people used to define a concept called as a polytropic efficiency. That means, if you recall the same expression that we used in terms of stagnation temperature and stagnation temperature pressures for compressors, and this is for turbine, that is T03 minus T04 in terms of pressure ratio P03 and P04. So, what if you look at these expressions, only difference that lies is that instead of gamma, we are representing that parameter as exponential parameter as n minus 1 by n, and that n minus 1 by n is defined in terms of polytropic efficiency, eta infinity C. Eta infinity C means it is a polytropic efficiency, C stands for compressor. Similarly, eta infinity T, that is polytropic efficiency for turbines. And of course, we can say that when you say compressor, it is for air, and when you say turbine, it is for hot gas. So, this gamma is also going to change. So, in a sense that by keeping polytropic efficiency same, one can, and also gamma has a realistic value for air and hot gases, we can have a value of n defined for, we can have a value of n. And for this reason a polytropic expression of polytropic efficiency has a better advantage when we compare the isentropic efficiency in a wide range of temperature and pressures for compressors and turbine. But more or less the physical meaning of isentropic efficiency and polytropic efficiency is same. Now, let us see that the how you are going to calculate the component losses, and it is a pressure loss. So, we have talked about compressor and turbine. Let us see what happens to pressure losses in heat exchanger. In fact, heat exchanger is also an important component, and these heat exchanger component losses are taken into account through pressure losses. So, what happens? The heat exchanger, when is normally incorporated, the main intention is to tap the heat from the exhaust from the turbine and has to preheat. So, in the process of the pressure losses in the passage of air side and gas side, there is a drop in the pressure, and we say delta Pb, and at the same time we have the pressure loss that is accounted due to air side and due to gas side. So, in a process that instead of landing at in this way, we take the pressure losses in the account, and the TH diagram slightly changes by taking these pressure losses. So, typical estimate that can come from the total pressure P naught 3 that enters to the turbine is equal to P naught 2 and 1 minus delta P b by P naught 2 minus delta P h a by P naught 2 and delta P 4 will be P a plus delta P h g. So, in both sides the pressure losses in air side, gas side it is taken into account, and P b that happens pressure loss in the combustion chamber, that is also taken into account. And over wide range of experiments, a typical number that has been generated, these losses are quantified are in the range of 2 to 3%, that is delta P b in the combustion chamber, it is the loss is about 2 to 3% for industrial plant and 6 to 8% in aero engines. And for heat exchanger side, delta PHA is 3% of the compressor delivery pressure, whereas in the gas side, because the low pressure, so we quantify in terms of is typically 0.04 bar. So, these numbers are we can use widely, or in a wide sense we can use and for our calculations. And again, moving from the heat exchanger, we also defined the heat exchanger's effectiveness to quantify the losses in our previous study, and there we expressed the losses in the heat exchanger as a function of effectiveness. So, as a parameter effectiveness or in the thermal ratio. Now, why do this effectiveness is required? Because the fluid can exchange heat through the separating wall alternatively or reject the heat exchangers are typically in the form of counter flow or cross flow, recuperator or regenerator, and the main fundamental process is here is that they have to tap the heat from the turbine exhaust, and they have to, by incorporating all the pressure losses, they must perform in a economic way. So, and another aspect is that if ideally if you use higher volume heat exchanger, it will have higher effectiveness, but then the cost will be high, because it is the cost is mainly determined by its surface area and volume. So, the cost will be high. So, economic size by incorporating and in order to have economic size heat exchanger, we must assume some effectiveness value, and that is limited in the range of 0.9. So, this is another way of quantifying the effectiveness of a heat exchanger component. Then we will move to the combustion efficiency. So, ideally speaking, while dealing with the combustion efficiency, we need some important parameters. First thing, we ensure that the combustion process is not complete, and typically a combustion, by assuming a combustion efficiency of 98 to 99%, we say that it is a incomplete combustion. Now, when it is incomplete combustion, then we should not combust the complete fuel. So, for which we have to find a ratio that is known as fuel air ratio, that is theoretical fuel air ratio for complete combustion to the actual fuel air ratio for the actual fuel air ratio, and that fuel air ratio represent as F. Whereas in the IC engine we call this as air fuel ratio or fuel air ratio, but in the gas turbine engines we mainly focus on fuel air ratio, because fuel is the most vital part as far as the particularly in the aircraft engines, because it is costly. So, based on that, one can define this combustion efficiency and in terms of net work that is produced and how much fuel we are going to consume in terms of fuel air ratio from its calorific value. So, Q net fuel from its calorific value. So, the total cycle efficiency can be also represented in this manner. Apart from that, there are some standard way of representing specific fuel consumption, normally represented as kg per kilowatt hour, where W that is equal to 3600 F by W net, where W net is represented in kg kilowatt second per kg. So, if you another way of representing that specific fuel consumption in terms of mass flow MF by divided by W net. By considering all these things, we can define the efficiency that is W net by F times Q net. Okay. In gas turbine engines, the other concept of using instead of efficiency, they call it heat rate. So, heat rate is nothing but we can relate between heat rate and efficiency, that is efficiency is equal to 3600 by heat rate, because heat rate is nothing but SFC into multiply by Q net. So, that is what the standard way of representation of combustion efficiency. Okay. So, this particular plot shows that in a real gas turbine engines how specific fuel varies with specific work output for a simple cycle and for a heat exchange cycle. If you see here, other parameter that was introduced, turbine inlet temperature was introduced with increase in the turbine inlet temperatures, and with increase in the pressure ratio you can see the specific fuel consumption drops. And that means if you operate a very simple cycle, we require very wide range of specific fuel consumption. But when you go for heat exchange cycle, for same power output, we have a very, the fuel efficiency has a very steady value, and of course we can play with wide range of turbine inlet temperatures and compression pressure ratio. So, these are the some characteristics curves that defines the specific fuel consumption variation with respect to specific work output. And of course, there is another table that talks about how you are going to calculate the fuel air ratio with respect to combustion temperature rise. So, I have taken a this plot is graphically plotted. I have taken it from the reference gas turbine theory from Sabramoto and Cohen and Rogers books, and what it says is that in a given problem you are supposed to find a fuel air ratio, but what you will be knowing is the terminal temperatures. So, this terminal temperatures are in particular in the combustion, we are represented as a combustion temperature rise. So, in a combustion chamber, the temperature rise is defined in the y axis, and for a given inlet air temperature that comes out from the compressor is drawn in this line. That means if you know this inlet temperature of air and if you know the combustion temperature rise, then you can easily plot what is the fuel air ratio. So, these curves talks about that how you are going to get the fuel air ratio graphically, and over wide range of operating temperatures these graphs has been plotted. So, graphically it is possible to quantify. Now, apart from this other type of loss, which is some simple losses, we can introduce the variation in the specific heats. As I mentioned, this temperature plays very vital role, and in the thermal circuit always the cycle temperature at different location changes continuously. Maximum cycle temperature could be as high as 1500 degree Kelvin. That point of time dissociation of air species plays a very vital role. So, because of this reason we say the specific value from the compressor side we take it as for air, when the specific heat value for turbine side, that is we call this as a combustion gases, these values are taken as this. So, Cp for air you can retain is 1.005 kilojoule kg Kelvin, and that for that gamma is 1.4, and for combustion gases we say Cp as 1.148 kilojoule per kg Kelvin and gamma is equal to 1.33. So, this particular plot says that how with temperature the Cp value changes and how the gamma value also drops. So, roughly that means with temperature the gamma value drops, Cp value changes. At some point down the line we have to assume some value, either you take the entire variation Cp as a function of temperature as well as gamma as function of temperature, or you take a consolidated average value that makes suitable justifications. So, in our analysis we will not say that variation with temperature, rather we will vary some two fixed values, one is compressor side, other is the turbine side. And last part is the mechanical losses. As I mentioned, always the compressor is driven by the turbine. So, there is a transmission losses in terms of bearing and windage. So, here only one process loss is permitted. So, for that reason the turbine compressor is nothing but ideally compressor power and turbine power equal, but in between there is a term what we call as a mechanical efficiency, and this mechanical efficiency is assumed to be 98 to 99%. So, okay. So, with this I have introduced all kind of component losses and how they are going to quantified. Now, with this particular problem, with this particular concept, let us see one numerical problem. So, the problem goes like this, is that here we are going to calculate, the problems are similar to what we have done in the earlier lectures, but here we are going to introduce the component efficiency and how they are going to be introduced, and in particular in terms of stagnation temperatures. So, this is how the philosophy is all about. So, a gas turbine engine, for a gas turbine engine we need to find out specific work of output, fuel consumption and cycle efficiency, and it is with the following data. Compression pressure ratio is 12, turbine inlet temperature is 1050 Kelvin, and we are given with isentropic efficiency for compressor 0.85, turbine 0.9, mechanical and combustion efficiency are given as 0.98, combustion chamber pressure losses as 6% of compressor delivery pressure, exhaust pressure loss is 0.03 bar, and ambient condition is 1 bar 288 Kelvin. So, for that let us draw the diagram first, that what are we are going to calculate. So, simple gas turbine circuit, we can have a compressor, and that is driven by a turbine, and we have a combustion chamber, and of course another thing is that with a free turbine, that means there is a free turbine, that means turbine is free, that means it is further expanded, the exhaust from the primary turbine is further expanded in another turbine, and we call this as a free turbine, that is for power generation. So, we can enter this, we can put the state point as 1, exit from the compressor as 2, combustion chamber entry as 2, and combustion chamber exit at 3, and first turbine exit at 4, and this is free turbine, or we say power turbine, and its exit is at 6, and here this is running, this shaft is running, power turbine drives the generator. So, we start with 1 and ends with 6. So, the condition, that ambient condition is 1 bar and 288 Kelvin, so we can write P1 as 1 bar, T1 as 288 Kelvin. Okay. And all to start these things, let us go one by one. First, compressor. So, for compressor we recall the working formula, that is in terms of stagnation temperatures. We can write T02 minus T01 is equal to T01 by compressor efficiency into P02 by P01 to the power gamma minus 1 by gamma minus 1. Now, let us see what are known to us. So, we can say P02 by P01 given to us 12. Compressor efficiency is 85%, that is 0.85. T01 is T01. Okay, so this T0 instead of T1 we have to say this is as a T01 because this is ambient condition, and here the static and temperature are same because ideally when it is ambient condition by default, so it is at 0 velocity. Similarly, we can say P01 is also P1. So that is the reason we say P02 by P1 is 12 and T01 is 288 Kelvin. So by putting this value we can find out T02 minus T01 as 349.1 Kelvin. So from this we can find out compressor work Cp times T02 minus T01, and these two are given. Cp we can take as 1.005 kilojoule per kg Kelvin, and we require the turbine work. So W T C, that means turbine that drives the compressor, is nothing but Wc divided by its mechanical efficiency, and this would be Wtc can be written as Cp by eta m into T02 minus T01. So by we all know Cp, we know mechanical efficiency as 0.98. So the turbine work that drives the compressor Wtc is equal to 358 kilojoule per kg. Okay. Then you come back to turbine side because you also have to know other pressure ratio and temperatures. So for turbine side we can write T03 minus T04 is equal to turbine efficiency into T03 whole bracket 1 minus 1 by P03 by P04 to the power gamma minus 1 by gamma. So here we say gamma g as 1.33 and Cpg also you have to take as 1.148 kilojoule per kg Kelvin. So here from this equation we know T03 as 1350 Kelvin turbine inlet temperature. We do not know this ratio, turbine efficiency 0.9. Then from this equation we all know all these parameters. So T03 and T04 are known. T04 is still not known. So to calculate T04 we have to take Wtp is equal to Wtc, turbine drives the compressor, that is Cpg into T03 minus T04. So we get this is a 350 is equal to 358 is equal to Cpg 1.148 into T03 minus T04. Okay, so this will give you T03 minus T04 as 303 Kelvin. So from this we can find out the ratio P03 by P04 as 3.15. Okay. Then moving further, what we also want to require P03 by P04, then we have to take the component efficiency. That means you have to go to combustion chamber. Pressure loss. That is nothing but 6% of compressor delivery pressure. That means 0.06 into compressor delivery pressure is 12 bar. So this turns out to be 0.72 bar. So obviously the P03 would be P02, that is 12 minus this loss 0.72, so it will be 11.28 bar. Now exhaust pressure loss is 0.03 bar. So P04 would be P04 would be 11.28 divided by 3.15 would be 3.58 bar. Okay, and here for the power turbine, that is P05 also you can find out. P05 would be 1 bar. So P05 one can find out, that is 1.003 bar, because P01 is 1 bar and we have to account the exit pressure loss of 0.03 bar. So P05 would be 1.0003 bar. So P05 is taken care. So you know P04 and 5. So from the for power turbine, we can find P04 by P05 as 3.58 divided by 1.03. So this is 3.47. Then we can write that T04 minus T05 for the power turbine as efficiency of this power turbine into T04 into 1 minus 1 by P04 by P05 to the power gamma minus 1 by gamma. So here gamma is 1.33. Okay, efficiency is 0.9. So all these numbers we know. Then we can, this will give you the T04 minus T05 as 250 Kelvin. So after having all these things, we need to calculate one by one what is specific work output. So specific work output WTP, one can find out Cp G T04 minus T05. First part, that is nothing but 287 kilojoule per kg. Second part, specific fuel consumption SFC, that is nothing but 3600 times F divided by WTP. Now to calculate F, we require this particular graph. We require this F. So for that we require the combustion temperature rise. So in our case, the combustion temperature rise delta T is nothing but T03 minus T02. So T03 and minus T02 we can obtain as 712.9 Kelvin. Already all those numbers we have calculated. So we know this, and T02 already we calculated as 637.1 Kelvin. So T02 for 637.1 somewhere here, and somewhere it will be here, and this temperature rise would be 712. So, if you can plot it, so this number F we can find out F as 0.024. So, putting this we can calculate SFC as 0.255 kg per kilowatt hour. So, we got the fuel consumption. The last part is cycle efficiency. So, cycle efficiency can be defined as 3600 divided by SFC into Q. So, Q we can say it is for fuel calorific value. So, we can say 443 megajoule per kg. So, this is a realistic number. By putting this, efficiency can be calculated as 0.32. Okay. So, this particular big problem helps you to get the complete understanding about a real gas turbine engine performance, and that involves calculations from the graphically, but that involves that some of the parameters needs to be referred in a graphical manner, and it will help you that how in a real gas turbine engines the component efficiencies are taken into account. So, this will help in the designing of a real gas turbine power plant. Okay, with this I conclude, and thank you for your attention.